Okay, so let's remember what we're talking about. Somebody tell me what we're talking about. Continuity, right? And what about continuity? Can somebody tell me about continuity?
The definition.
Yeah, somebody give me one or the other definition, or both.
So if you can control the distance between x values such that x naught minus x n minus x naught is less than 7. And that's not so.
Okay. So you're remembering some of the words, right? You're remembering some of the words, but try to string it in the right. More important than remembering the details first is to remember the idea, right? Get the sort of like the intuitive feel of it, right? So I think what you're going for is the epsilon-delta idea, right? It's the epsilon-delta picture. So, right. So here it is, right? Your function. Here's a c, right? Your function is continuous. Here's your picture. Your function is continuous at f of c, right? And what this means is that if somebody wants you to stay between here and here, so you notice, you look at the picture and you say, well, look, if somebody wants me to stay between here and here, I can find a neighborhood of C in which that happens, right? I can find a neighborhood of C in which that happens. Look, if I choose this neighborhood, everybody in here stays between the bars, right? And you notice that, maybe suppose that's one epsilon. Somebody takes a different epsilon and says, I'd like you to stay between here and here. And you say, okay, well, I can find a neighborhood of C in which I stay between those bars, right? And no matter what epsilon is given, you can find a neighborhood of C in which that neighborhood is, in which that tolerance is satisfied. Okay, right? So that's the sort of intuitive picture. One version of the intuitive picture. Another way of looking at it is like this. Instead of drawing the axes perpendicular to each other, let's draw them parallel to each other, and think of f as a function going from here to here. Okay, so here is C, and here is f of C. Okay, and the game that we're playing, if we look at it this way, is like this. You say, well, look, somebody gives you a neighborhood around f of C, so somebody gives you a neighborhood of f of C, and we were able to find a neighborhood of C. There was a corresponding delta neighborhood of C where everything in that delta neighborhood got mapped into the epsilon neighborhood, right? Everything in the delta neighborhood got mapped into the epsilon neighborhood, right? And more than that, when somebody gave us a tighter neighborhood, somebody gives another neighborhood, this one epsilon prime, say, of f of C, we were able to find a neighborhood of a different delta neighborhood of C, different neighborhood of C where everybody gets mapped into that one. And you're able to do that for every epsilon. Okay, no matter what epsilon neighborhood you're given here, there's a delta neighborhood that gets mapped into it, right? Where all the points inside here go inside there, right? And that's the same thing as this picture here, right? No matter what bars are chosen, around f of C, evenly spaced above and below, you can find an interval around C in which all the outputs lie between the bars. Okay, so these two are exactly the same picture, but just drawn. One is drawn as a graph, and one is drawn as a map. these integers. Okay, and then so that from the picture you get the one of the definitions. So one of the definitions is given any epsilon, right? Given any epsilon, there exists a delta so that if x lies in c minus delta, c plus delta, right? People usually write this in the, if x minus c is less than delta, then f of x minus f of c is less than epsilon. Right, and sometimes people write delta and make the dependence on epsilon clear. Right, this delta will change as the epsilon changes. So this is sort of corresponding to the upper picture. Right? But you see, the upper picture and the lower picture are the same thing, because to say x minus c is less than delta means that x lies in the delta neighborhood of c. Right? To say f of x minus f of c is less than epsilon is the same thing as saying that f of x lies in the epsilon neighborhood of f of c. Right? So the upper picture and the lower picture are exactly the same thing. Right? The definition, you can use this definition to talk about either one. Right? But if you wanted to rewrite it in a way that was sort of more, more neighborhood centric, you'd say given any neighborhood of f of c, where epsilon is greater than 0, there exists a neighborhood of c such that f of the neighborhood of c is contained in the neighborhood of f of c. Right. So I'm really just rewriting this thing from the neighborhood point of view. And so that's what continuity means. Okay. Somebody is missing. Who is missing? Oh, yeah. Okay. Let me ask you a question. Does this look similar to something else? This should look very similar to something else. What? Limit, right? What's the difference between this thing and limit? This definition and the definition of limit. Right, this looks pretty much like the limit of f of x as x approaches c is f of c. What's the difference between the definition of limit and the definition of continuity? Right, this sort of looks like, so remember what it meant to say that something had a limit of L. It meant that for all epsilon greater than 0, there exists a delta such that if x minus c is less than delta and greater than 0, then f of x minus L was less than epsilon. Okay. That's the definition of limit. What's the difference? Mia, yeah. John, you're nodding. What's the difference? No? You're nodding at Mia?
Isn't that
Yes.
L isn't necessarily of the form f of L?
That's part of it. That's part of it. But but the more crucial part maybe is Ron.
Is it that delta is not positive? That's great effort.
The delta?
Yeah.
Yes. No, it still is a function of epsilon. It's still dependent on epsilon. As the epsilon changes, the delta changes. But
I don't know.
anybody? Okay. Just look at it. There's a very clear, just physical difference here. Zero, right? Right. There's a zero here. Right. There's a zero here, right? With the epsilon, with the limit, right? X minus c has to be. We don't say anything about. We don't say that this has to be if x. We don't say anything about x equaling c. Right? We don't care about x equaling c, which corresponds to the fact that when you're talking about the limit, the value at c is not under your control. Right? But here we're saying that this had better be true. That this had better be true even when x is equal to c. Right? So here, this is going to be true except at x equals c. We don't require anything about x equaling c. We don't require anything to happen when x equals c. But here we do, right? That this had better happen even for x equals c. Okay. Okay, so that's one definition. That's the epsilon-delta, right? This is the epsilon-delta definition of continuity. And then we have the other definition of continuity. Does anyone remember that? Does anyone remember that one? So, you have some function from some domain, right? And you have some point C in the domain. We say f is continuous at C if what happens? Can you remember? Yeah. I was just talking the other day, but no one remembers. It's okay. You have a lot on your minds. Something to do with sequences. What is it?
It's like if there's a sequence that converges to C in a domain, then the function of that sequence converge to the f of C.
Yeah, great. The auditing student gets it. If given any sequence in your domain such that xn goes to C, we have f of xn converges to f of c. Right? So this is your sort of your old-fashioned definition, right? That as if you take any sequence that gets closer and closer to C, then the outputs of that sequence get closer and closer to f of c. Then the outputs, right? So each of these guys has an output, right? And these outputs, if the inputs converge to C, then the outputs converge to f of c. Right. So that's drawing it graphically. Right. If we drew it in the map way, it would look like this. Right. Here is C. Here is f of c. Given any sequence of points that converges to C, the outputs, the image of those points, the images of those points, so x1, x2, blah, 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 then the images f of x1, f of x2, blah, 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 have to converge to f of c. And so those are the two ways of defining limits. Defining continuity, and this one is normally called sequential continuity, and the other one is called continuity. Okay. So Yeah, so let's actually show that these two definitions are the same. So theorem, there's a function of p to r, and let's just for convenience, let's just think that we're going from r to r. That'll make it a little bit easier. You don't have to keep track of our neighborhood being inside the domain. Yeah.
Provide the context. So what are the context?
Yeah. Don't worry. I'll finish writing it in a second. So you have some function from r to r, and you have some point in r. Let me call it x naught. That's what it is in minutes. Okay. We want to show that the claim is that f is continuous at x naught, if and only if f is sequentially continuous at x naught. In other words, given any sequence converging to x naught, we have f of x n converges to f of x naught. So think about it for a minute and see if you can come up with some, which way do you want to do first? Forwards or backwards? Go forwards. Why did I even ask you? You guys going to decide. We're going to go forwards. So see if you can think of how this makes sense, right? You know that f is continuous at x naught. In other words, given any epsilon neighborhood over here, you can find a delta neighborhood that gets mapped inside it. Right? And you want to show that given any sequence converging to x naught, then the image sequence converges to f of x naught. Right? So what does that mean? You want to show that given any epsilon, right? Given any epsilon around epsilon neighborhood of f of x naught, there's a time past which your sequence, the images of your sequence points all lie inside that epsilon neighborhood. Right? So if you say it that way, maybe it's completely obvious. show this sequence converges, in other words, that we can play the epsilon endgame successfully. So, big success. Somebody tell me about how we're going to find our n. Remember what we have? Yeah, look. Yeah, yeah, very much, very much. So let's you know, since f is continuous at x naught, right? So right. So anyways, x naught. Since f is continuous at x naught, we know we can play the epsilon-delta game successfully, right? So there exists a delta such that f of anything inside the delta neighborhood of x naught lies inside the epsilon neighborhood of f of x naught, right? So we know we can find the delta. So that everybody inside here lies inside here, right? Okay, so how does that give us our n? We want an n so that, you know, if n is bigger than n, then everybody, all the f of xn's lie inside it. All the f of xn's lie, all the f of xn's lie inside it. So we have a delta, right? So that if you drop into this neighborhood, all the outputs will lie inside here. Right? So right? So tell me what to write. I mean, is the picture clear? John, you said done. So tell me what picture you have in your head. What's going to happen? We want to get an n. We want to get a time past which all the outputs lie inside there. Delta is chosen. Delta is chosen. So we've chosen epsilon. We got a delta.
Then you know for sure that the output
As long as the inputs are in here, right? Right. So how do we get the inputs in here? Why do we know that the inputs can be made to lie inside here past a certain time? Because no, not because of continuity. Not because of continuity. Like, what do we know about our sequence? Right? Well, do you get it? No. Mia, do you get it? No. Okay.
Which direction are we going?
Forwards. Forwards. We're trying to show that if we have continuity at x naught, then we have sequential continuity. In other words, given a sequence, so we have some sequence that converges to x naught, and we want to show that the outputs of that sequence converge to f of x naught.
So why are we trying to show that they converge to? Why are we still trying to show this side of it's given?
I'm gonna run over the whole thing again. So we're trying to show that f is sequentially continuous. Right? What does that mean? That means that given any sequence that converges to x naught, then the outputs are going to converge to f of x naught. So take some sequence. Take some sequence. We want to show that the output sequence, the image of that sequence converges to f of x naught. What does that mean? What does it mean for a sequence for this sequence to this to converge to this? It means that we want to be able to play the epsilon endgame for this sequence. Right? We want to be able to play the epsilon endgame for this sequence. In other words, given any epsilon neighborhood of f of x naught, we want to find a time past which all the f of x n's lie in that neighborhood. Right? That's what convergence of the sequence means. Right? Making play the epsilon neighborhood. Right? That given any epsilon, there's a time past which everybody lies in that epsilon neighborhood. Okay, so that's what we want to show, right? We want to play the epsilon n game. So what do we want to do? We want to show we can find n if we're given epsilon. Okay, so how do we find n? How do we? Well, let's take the epsilon. Let's take an epsilon. What we have are two things. First, that f is continuous at x naught, right? And second, that xn converges to x naught. So those are two things that we have. So f is continuous at x naught. What does that mean? That means that since we have this epsilon neighborhood here, there's a delta neighborhood of x naught, so that everything inside here gets mapped to delta. That's what we have, right? And we also have that the xi's converge to the x naught, right? Right? So that is, we can make our xi's as close to x naught as we want, right? So maybe seeing how the pieces fit. John, yeah. 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 So how do I choose my n? How do I choose my n? In the delta neighborhood, exactly. Yeah. In the delta neighborhood, right? So you think, well, since xn converges to x naught, there's a time past which x n minus x naught is smaller than delta, right? So there's a time past which all the guys lie in the delta neighborhood. Well, in that case, f of x n minus f of x naught is smaller than x naught, right? Because we chose the delta neighborhood using the definition of continuity, right? So that everybody inside here gets mapped is there. You choose a time. Since these guys converge to x naught, you can choose a time past which they all lie inside here. Well, if they all lie inside here, that means all the images lie in the epsilon neighborhood, right? And so we're done. Right? So what have we done? So what have we done? We've shown that given any epsilon, blah blah blah, they exist at time such that if n is bigger than n, f of x n and f of x naught is smaller than epsilon. In other words, the limit of f of x naught equals f of x n is f of x naught. So, and since we did that for an arbitrary sequence, we've got sequential approximation. So what I'm writing over here is just sort of like an overview of this. Right? We showed that given any epsilon, there's a time past which these guys are within epsilon of f of x naught. That means f of x n converges to f of x naught. And that's the definition of convergence. So you don't really need, this last part is just sort of a commentary. Basically, at this point, you're done. then maybe after that I understand. Yeah, it was actually famous for like getting to the library first thing in the morning and getting kicked out of the library at the end of the day. To the extent that they say that after I graduated from college, that I had still appeared there even afterwards. Because I always use the same seat. I always use the same seat. Yeah, so like during the weekends, you had to sign in. You had to sign in your name, and apparently, like after I left, people continued to sign in my name, just because they were so used to seeing my name on the list. Okay, oops, we actually it's up. We haven't done the opposite direction. So now let's go backwards. Backwards, right? So, you're given this property of sequences. You know that given any sequence, so we've given any xn that converges to x naught, we know we have that f of xn converges to f of x naught. And we want to show that given any epsilon neighborhood of f of x naught, there exists a corresponding neighborhood of x naught such that f of that corresponding neighborhood lies inside of the epsilon. I'm going to do this one by contradiction. So suppose there is a bad epsilon. Suppose there's a bad epsilon. And for this epsilon, there's a bad epsilon neighborhood. Suppose that for that bad epsilon neighborhood, there's no delta neighborhood that works. That would be the logical negation of this. Suppose there's a bad epsilon neighborhood for which no delta neighborhood works. That's colloquially what it's saying. In other words, suppose there exists an epsilon naught such that given any neighborhood on and so forth.
And then the neighborhood has to be rhythmically converged.
It doesn't matter. It doesn't matter. All you want is that the sequence converge to x naught, right? So if the first guy is within 1, the second one is within a half, the third is within a third, the fourth is within a fourth, they're going to converge to x naught.
The key case is neighborhood X naught.
Exactly. Yeah. So here's our first one, here's our second one, here's our third one, right? And in each one, you know that each one fails, so there's some point inside there that gets knocked outside of the bad epsilon. And so you've got the sequence that converges to x naught, but all the images lie outside the neighborhood, and so the images don't converge to f of x naught, because they're all away from it. Right? They're all fixed distance away from it. Right? Like what we created is x naught converges to f naught, but f of x naught does not converge to f of x naught. Right? And so we don't have sequential continuity contradiction because we assumed that we did have sequential continuity. Okay, in the last 2 minutes, let me see if I can, well, there's no point. Okay, so I was going to do some examples, but okay, I'm gonna let me see if I can do an example. Okay, so examples 1, f of x is 2x plus 1 is continuous everywhere. So the simple one. Proof via sequences. So suppose we want to use the sequential limit definition. So suppose xn converges to x. We want to show that f of xn converges to f of x. Well, f of xn is 2xn plus 1. Right? And the limit as n goes to infinity of 2xn plus 1 is, by the limits and arithmetic theorem, is 2 times the limit of xn as n goes to infinity. Well, that's going to be 2x plus 1. Maybe I should call these guys not keep it consistent. So that would be the end, right? We've proven sequential continuity for this function. So that would be one way of proving it. And we're using the machinery that we built earlier, the limits and arithmetic. Yeah, Epsilon-delta, we say, so let x naught be an R. So we want to show that yeah, there's no time. Okay, sorry, I'll do it on